Today, we're diving into a really cool idea, one that could completely change how you look at everything from stock market crashes to system failures. It's all about finding these secret signals that are hiding in plain sight, inside what we usually just write off as error. So let's just jump right in with a massive question. What if the error in our models, that random noise we work so hard to get rid of, isn't an error at all? What if it's actually the most important signal we've got? To really get our heads around this, we have to talk about the problem with the word error itself. And to do that, I want you to meet beta, kind of the misunderstood hero in almost every scientific equation out there. So, scientists and data folks use this simple-looking equation all the time to predict things. It starts with G, which is just the outcome we're trying to forecast. Could be anything, right? A company's growth, the path of a storm, you name it. Then you've got F of P. Now this part represents everything we think we know, all the predictable stuff, all the factors and parameters that fit nicely into our neat and tidy theories. And then there's beta. This is what's left over. For decades, we've just called this error or noise. It's the messy, random, unpredictable stuff that our perfect little model can't explain. So what do? We ignore it. We try to sweep it under the rug. But what if that's where we've been missing the entire story? And this brings us to a really radical idea. What if we stop treating beta like garbage and actually start listening to it like it's a signal? I mean, that one little shift in thinking changes absolutely everything about how we predict big, important events. This one sentence from the paper we're looking at just nails the whole idea. It says, we should recast beta not as formless error, but as a structured anomaly tied to the onset of emergence. Emergence is just a fancy word for a huge, fundamental change in a system. This right here is the aha moment. Beta isn't random junk. It's a structured warning sign. Now, to understand that warning sign, you need one more concept. It's called the viability manifold, or just VEN. Think of it as an invisible boundary, a tipping point. It's the line a system crosses right before its behavior totally changes, like water hitting 212 degrees Fahrenheit and starting to boil, or that moment right before you step off the edge of a cliff. Okay, so if beta is a warning that we're getting dangerously close to this tipping point, what does that warning actually look like? Or, sound like? Well, it turns out it comes in two very distinct flavors. Two different ways a system can tell us it's about to break. The first flavor is called the deterministic spike, and the name itself gives you a pretty big clue. It's predictable. A deterministic anomaly is like this rising hum of danger. As a system gets closer and closer to that tipping point, the error starts to spike in a way we can actually track. The signal gets louder in direct proportion to how much danger you're in. The perfect analogy is a Geiger counter. The closer you get to a radioactive source, the faster and louder it clicks. It's a clear, continuous, growing warning. But not all warnings build up like that. The second flavor is way more startling. It's called the stochastic jump. Now, this is a whole different ballgame. It's not a gradual spike. It's the potential for a sudden, massive event. So as you get closer to the tipping point, the signal doesn't get louder. Instead, the chance of a catastrophic jump happening just goes way, way up. The best analogy for this? It's like walking through a minefield. You might take 10 safe steps, 20 safe steps, but you know that with every single step deeper into that danger zone, the probability of a sudden, catastrophic explosion is increasing dramatically. So putting them side by side really makes it crystal clear. The deterministic spike is that continuous signal getting louder, like our Geiger counter. The stochastic jump is all about the rising probability of a huge one-time event, like that minefield. One is a predictable roar. The other is a terrifying silence where the risk is just silently building up. Okay, so this is all fascinating theory, right? But how do we actually use it? Well, the source material gives us a super practical 5-step guide for finding these hidden signals in our own data. All right, let's walk through this. Step 1 is simple. You find the residuals. That's just isolating that leftover error we've been talking about all this time. Step 2 is where the magic starts. You diagnose those errors. You become a detective. You're looking for clues. Is this stuff truly random, or does it have the character of a Geiger counter or a minefield? Rare, bursty spikes. If you find a pattern, you move to steps 3 and 4. Here, you model the hazard and the jump size. You're basically asking, what conditions make a big jump more likely, and just how big is that jump when it happens? And all of that hard work leads to step 5. You reinterpret the whole story. You're not trying to get rid of the error anymore. You're building a brand new model that actually expects these structured jumps, giving you this incredibly powerful way of seeing what's coming around the corner.
So, why does all this matter? I mean, this isn't just some new statistical trick. Adopting this way of thinking, it fundamentally changes how we see the world and the very nature of change itself.
This way of thinking gives us 4 really profound takeaways. First, big changes in the world are often sudden jumps, not these smooth, gentle curves that we can easily predict from the past. Second, what we call noise isn't random at all. It has a cause, it has a character. Third, that tipping point, the fold, is a singular event. You can't just deduce it from what came before. And finally, and this one is my favorite, it changes how we think about time. We move away from chronos, time as a steady, ticking clock, and toward kairos, which is the idea that time is really defined by singular, critical moments of change that alter everything that comes after. When you really boil it all down, this entire shift in perspective means we're moving from just trying to predict an outcome to actually understanding the anatomy of surprise itself. We're no longer just forecasting what's going to happen. We're decoding the very structure of how things break, how they change, and how new things emerge. And that brings us to the final thought here, because this idea isn't just for scientists or data analysts. It's a lens for looking at pretty much anything. So I'll just leave you with this question. What's the noise in your own life, in your career, your health, your relationships, that might not be noise at all, but a signal for what's coming next?